Hey everybody, and welcome to our next video, which is all about formal charge and resonance. So in our last video, and I'm just going to show you up here, you might have heard me say, well, some of these structures look a little funny, right? Especially this one, I think it was. Why does it have the ability to bond like that? I thought chlorine has 3 lone pairs, not only 2. We're going to talk about why this is okay in this case. And it's all based on something known as formal charge, right? So when we are drawing these Lewis dot structures, we also have to familiarize ourselves with formal charge. And this is going to help us predict the best choice for Lewis dot structures. So at this point, you might be between a couple of Lewis dot structures. You might say, wait a minute, Mrs. Snyder, is this the correct Lewis dot structure? Or is this the correct Lewis dot structure? And from this point on, I will say, well, what are the formal charges for all the molecules in that structure? Because that is what's going to tell you what the best structure is. And that's because atoms with lower formal charges lead to more stable structures. And the formal charge is going to tell us whether the atom has more or less electrons than it normally would. And typically, your negative formal charge is preferred on more electronegative atoms. So those electronegative atoms, of course, want electrons more. So in that case, if it has a negative formal charge, that means it has more electrons than it technically should. So there's a very easy equation. It's not even an equation. It's just how to calculate the formal charge. So we can determine the formal charge for an element in a Lewis dot structure by taking our number of valence electrons and subtracting the number of bonds, and by subtracting from that the number of lone electrons. And notice it says electrons, not lone pairs. So it's how many lone electrons are there. So if you have 1 lone pair, you would have 2 lone electrons. Rather than talk about this more, we're just going to do some examples, right? So in this case, it says calculate the formal charge on oxygen in the hydronium ion. So let's go ahead and actually draw the Lewis dot structure for hydronium. Hydrogen has 1 valence electron, 1 electron, period. There's 3 of them, so that means I have 3 electrons. Oxygen has 6. Add them up, I have 9. But I have to remember that this whole entire structure has 1 more proton and electron. So I actually have to subtract an electron. And there are 8 to place in total. Oxygen is going to go in the middle because hydrogen never does. And let's start keeping track of our electrons here. 2, 4, 6. Looks like I got 2 electrons to place. I'm going to put them on hydrogen or on oxygen right there. And remember, whenever I have something that has an overall charge, you should write that Lewis dot structure in brackets and then put the charge on the outside. So it's asking here, what is the formal charge on oxygen? Let's use this equation up here and calculate it. So I put it up on the screen so we could see. Formal charge is equal to the number of valence electrons. So we know oxygen has 6 valence electrons. So we'll do formal charge is equal to 6 minus the number of bonds. And this oxygen has 1, 2, 3 bonds to it. So I'll do 3 bonds minus the number of lone electrons. So this has 1 lone pair, which means there are 1, 2 lone electrons on oxygen. So I'm going to do minus 2 electrons. And you find that that oxygen has an overall formal charge of positive 1. This is why this whole structure has a charge of positive 1. Each of these hydrogens has a 0 formal charge. It's got 1 valence electron, it's got 1 bond, it's got no lone electrons. 1 minus 1 is 0. However, this charge on the outside is the sum of all of these charges. So 0 plus 0 plus 0 plus 1 gives me 1. And that's why we put that +1 on the outside. It's the sum of all those formal charges. And in this case, it is also just the formal charge on oxygen. Let's take a look at this OPCl3. We actually drew this up above, right? So, and I said, okay, with your wisdom, right, you would know that oxygen has to have a double bond. Well, why is that? Well, it comes down to its formal charge. It says, which structure is the best choice for drawing the Lewis dot structure and why? Let's go ahead and count these structures here. Looks like we are missing something in this one too. Not that it matters, because we could, actually I'm gonna eliminate that there, because it works out anyway, because this one's wrong to begin with. But we'll make use of it. Phosphorus, let's count its formal charge. So phosphorus, we'll make a list, has 5 valence electrons, minus, it's got 4 bonds, and it has no lone electrons. So phosphorus, in this example, has an overall formal charge of -1 or +1. Let's count oxygen next. Oxygen has 6 valence electrons, -1 bond, minus 1, 2, 3, 4, 5, 6. 6 minus 1 minus 6 is overall -1. And if you were to consider this guy down at the bottom, right, because these two look pretty normal, they look good. Chlorine's got 7 valence electrons, -1, minus 1, 2, 3, 4, 5. In fact, this one also has an overall charge of +1. And I don't think it's meant to be like that. I think it just copied weird, but we'll just make use of it there. As opposed to, let's count our formal charges on this structure. So phosphorus, again, has 5 valence electrons, minus 1, 2, 3, 4, 5, minus, it has no lone electrons. So phosphorus here is a formal charge of 0. Let's try oxygen. Oxygen's got 6 valence electrons. I'm going to subtract 2 for 2 bonds. And I'm going to subtract 4 from those lone electrons, and I get 0 again. And this chlorine is much better this time. But this structure on the right is the much better choice, and that's because we have the lower overall formal charges. Atoms want, or molecules will adopt the structure that minimizes its potential energy. And to minimize its potential energy, it wants to have the lower formal charges. This case, the one on the left, I have way too many formal charges. These atoms are not that stable. And their phosphorus is not that stable. It's got 1 more proton than electron. Oxygen has an additional electron. It's got a lot of weird stuff happening. This one on the right, however, is good. And that's because it has formal charges of 0. They're very happy the way that they are. Let's use that and just calculate the formal charge for each atom that's being pointed to. So in this case, the nitrogen. Calculate the formal charge here. Nitrogen, we know, has 5 valence electrons. From that, I'm going to subtract how many bonds. So let's get us 1, 2, 3, 4 bonds. And this nitrogen has no lone pairs. So my overall formal charge on that nitrogen is +1. Let's try this nitrogen off to the side. This nitrogen still has 5 valence electrons. This nitrogen has 1, 2, 3 bonds, minus, it's got 2 lone electrons. This nitrogen has an overall charge of 0, a formal charge of 0. So if we were to say which one of these structures is more sound, it would be the one on the left, right? And that's because nitrogen has a formal charge of 0. That's what we strive to get, it's a formal charge of 0. Oxygen, it's like we have 6 valence electrons, minus, it's got 1 bond going to it, minus 1, 2, 3, 4, 5, 6. Overall formal charge is -1. So this oxygen is not that stable the way that it is. But this one's not entirely too unhappy, and that's because oxygen doesn't mind having an overall formal charge of -1, and that's because oxygen is very electronegative. Let's try this one here. So carbon's got 4 valence electrons, minus 1, 2, 3 bonds, minus 2. This carbon has an overall charge of -1. And you might recall, Mrs. Snyder always said carbon's never going to have lone pairs, right? Carbon never has lone pairs. And the reason why is because its formal charge is not going to be 0. It's very unstable. This whole process is not hard, this formal charge, but we do have to use this a lot of times to determine which structure is the better structure, if I have a few examples of them. So let's now talk about resonance, right, which also has to deal with structures. What makes one structure better than another? Let's get the marker back here. So resonance is, let's get the colors that we like here, is a way of describing bonding in certain molecules or ions by the combination of several contributing structures into one resonance hybrid. Oof. So here's an example. Okay, here's the nitrate ion. Okay, we know nitrate to be NO3 minus 1. Let's draw this here, NO3 minus 1. If you were to draw this Lewis dot structure out there, you would find that you would get one of these particular structures. And notice how that -1 is on the outside of the brackets. Might ask you, okay, well, what is the overall formal charge? Actually, let's do that. Let's determine the formal charge of each atom in here. Nitrogen's got 5 valence electrons, minus 4 bonds, minus no lone pairs. So this formal charge is +1. Oxygen, this has a formal charge of 0. And these oxygens actually each have a formal charge of -1. But if I add them up, -1 + 1 - 1 gives me an overall formal charge of -1. So that's how we get this number on the outside, remember. Anyway, if you look at all of these structures, okay, I'm going to delete these things here just because I wanted to show you that quick. But these look like they're the same molecule, but they're not. And if I look at these 3 resonance structures, these are 3 different representations of the same exact molecule. So if I just consider this bond right here, in this molecule, this bond is a double bond. But in this molecule, that same bond between that same exact nitrogen and oxygen is a single bond. And here, it's a single bond. These are not identical structures, okay? They kind of are, but these are called resonance structures. Each of these contributes to the actual structure that it actually is, okay? Very weird concept. Let's take a look at another one of these bonds. So I have this nitrogen and oxygen bond. This bond is a single bond, but here it's a double bond, and here it's a single bond. So only in this center structure does this particular bond have a double bond. And lastly, let's consider this last bond. Here I have a single bond, here it's a single, and there it's a single, or there's a double, I'm sorry. Each of these structures is showing a different arrangement of the bonds between each oxygen and the nitrogen. Although on paper they look the same, they're actually very different because you have to consider each individual atom, okay? Now, these are the different resonance structures of the nitrate molecule. And you'll notice that resonance is shown or denoted by this right here, okay? This is what we call a resonance arrow. resonance arrow. It's like a double-headed arrow, like that. But in real life, neither one of these exists, okay? In real life, we actually have a combination of all three of these resonance structures. So none of these exist, okay? I'm just going to cross that off. None of them technically exist. A hybrid is like a combination of more than one thing, right? If you have a hybrid animal, like a mule is like a donkey and a Z, I have no idea, right? But, or a horse and a donkey, something like that. None of these ones actually exist. So when you have like the child of them, it's not a donkey and it's not a horse. It's something totally new. So this is the hybrid of these right here. This is a combination of all of these resonance structures. So this is a combination. And this is what actually exists. You would be asked, however, to draw all of the resonance structures that contribute to the one structure, okay? We'll do some examples with this in a little bit. So here's a multiple choice question that I found that I think is a great example. So it says, which of the following statements, if true, would support the claim that the nitrate ion has three resonance structures, okay? So we have these examples right here. And I'll just give you the answer first. The answer is actually A. The nitrate ion is not a polar species. And that's because if all three of these bonds were exactly the same, which is shown here, right? I have this full-on single bond, and then I have just like a partial double bond for each of these. If I look at this resonance structure, this is nonpolar, right? I have an equal pull in all three directions coming from that nitrogen. In this case, if this resonance structure theory was correct, right, my overall structure would be nonpolar, okay? The oxygen, nitrogen, oxygen bond angles are 90 degrees. Oxygen, nitrogen, oxygen bond angles are 90 degrees. Well, if you remember anything from Chem 1, this is a trigonal planar molecule, and you could see that the bond angles here are much greater than 90. In fact, they're 120, so that one can't be correct. I like C and D because I think that this really goes to show like what resonance actually means. If all three of these bonds in this nitrate structure were all technically the same, right? Because remember, all of these three exist in one. So here's our single bond and here's our partial double bonds that exists on all three of them, technically. But it's just like a partial there. If these all have the same type of bond, a partial double bond, none of these bonds is longer than another. They're all the same exact length because they're the same type of bond between the same different types of atoms. So in this case, one of the bonds in nitrate is longer than the other two? No. One is shorter than the other two? No. They should be the same. And that's because if I have the same type of bond between all of these, why would one be longer than the other? Or why would one be shorter than another? Right? When they're all the same type of bond, they should be the same exact length. So your answer is actually A. I thought this was a really good question to just kind of show this. And remember, if you're like, what the heck is she talking about? We're going to practice with this. So don't worry. Don't get all worked up about just this one question. It's always good practice just to see. Draw all the resonance structures for ozone. So ozone has, let's count the number of electrons. It's got 6 times 3. 6 electrons times 3 oxygens. I have 18 electrons I have to place. So I'm going to draw this guy right here. And let's go ahead and start drawing. The way I did this was I just put a straight line. Right, it's good enough. So you have 18 electrons minus 4 gives me a total of, 14 electrons left. This is how the structure actually looks. But if you try this out, right, there's 6, gives me 8. 1, 2, 3, 4, 5, 6. There's 8 right there. Now, you can count the formal charges, because if you were to do another structure for this, let's say you did this, you would see that your formal charges are too high. So let's take a look. This oxygen has a formal charge of 0. Let's do this in a different color here. 0. This oxygen, so 6 minus 1, 2, 3 gives me 3, minus another 2 gives me plus 1. This oxygen right here, 6 valence electrons minus 1 gives me 5, minus another 6 gives me minus 1. So notice how the sum of all my formal charges gives me 0, which works out because O3 is not charged. Let's take a look at this one. Formal charge on each of these is 0, but my formal charge on this middle oxygen, 6 minus 4, gives me plus 2. This structure can't work, and that's because I have an overall charge of plus 2. I can't have that. It has to have a formal charge of, or an overall charge of 0. So this structure is wrong. So I'm going to redraw this one actually, because it's kind of tucked away over there. So I have right there, there, here. So we want to draw the resonance structure. And in fact, there is only one. So I'm going to draw a double-headed arrow. And I'm just going to take this and draw the mirror image of it. So notice how on this one right here on the left, my double bonded oxygen is on this side. In my resonance structure, that double bond would be on the opposite side. So I'm just going to take it and draw the mirror image just like that. And that is the only resonance structure that I would have. And that's because there's only 2 bonds. So 2 bonds signifies 2 resonance structures. Not saying that that's always the case, but a lot of times it might be. And that's it for resonance structures. Again, this is not the easiest thing in the world. We're going to get some practice with this in class, but especially in this video, I'm trying to keep everything short so we do lots of practice problems in class. As always, if you have any questions, let me know. I will see you in the next video. Bye.